The universe is whispering to us, and we're only just beginning to understand what it's saying. Out there, hidden in the vast darkness between the stars, strange signals ripple through interstellar gas clouds, mysterious pulses, unexplained bursts, and eerie patterns that defy everything we know. Scientists have spent decades trying to decode them, but these cosmic enigmas refuse to give up their secrets. Some vanish as quickly as they appear, while others repeat in ways that make no sense. Could they be natural phenomena we've yet to discover, or something far more extraordinary? Today, we're diving into 50 of the most baffling signals ever detected, each one a puzzle piece in the grand mystery of the cosmos. From the infamous WOW signal to bizarre radio whispers from distant galaxies, these anomalies challenge our understanding of space itself. And by the end of this journey, you'll see why these interstellar riddles might just hold the key to unlocking the universe's deepest secrets. So buckle up, because what we're about to explore will stretch your imagination to the very edges of reality. Now, let's turn our attention to one of the most famous cosmic mysteries of all time, the WOW signal. Detected in 1977 by the Big Ear radio telescope in Ohio, this brief but powerful burst of radio waves lasted just 72 seconds, yet it left an indelible mark on the search for extraterrestrial intelligence. What made it so extraordinary? For starters, it hit a frequency of 1420 MHz, a range scientists had pinpointed as ideal for interstellar communication, since hydrogen, the most common element in the universe, emits energy at that wavelength. The signal was so intense that astronomer Jerry Amon circled it on the printout and scribbled "WOW" next to it, giving the phenomenon its iconic name. Decades later, we still don't know what caused it. Some argue it could have been a natural cosmic event, like a comet's hydrogen cloud reflecting sunlight, except no known comet was in that part of the sky at the time. Others speculate it might have been an alien transmission, but if so, why hasn't it repeated? Despite countless searches, the WOW signal remains a one-off, defying every attempt at explanation. Its brevity and singularity make it both tantalizing and frustrating, a cosmic flare that flickered once and vanished, leaving us with more questions than answers. Could it have been a glitch, a natural anomaly, or something far more deliberate? The mystery endures, reminding us just how much we still have to learn about the universe's hidden voices. Shifting our gaze to the present, modern science hasn't given up on unraveling the WOW signal's secrets. In recent years, advanced telescopes like the Allen Telescope Array and the Breakthrough Listen project have trained their sights on the same patch of sky, hoping to catch a repeat of that elusive burst. These efforts use cutting-edge technology, machine learning to sift through radio noise, ultra-sensitive receivers to pick up faint whispers from space, yet the signal has never reappeared. One intriguing theory suggests the WOW signal might have been a one-time cosmic event, like a distant star's magnetic flare or a rogue asteroid's brief interaction with interstellar gas. But here's the catch: even these explanations fall short. No known natural phenomenon matches its precise frequency and intensity. The more we learn, the more the WOW signal stands out as an outlier, defying categorization. What makes this mystery so valuable isn't just the unanswered question. It's the lesson it teaches us about the universe's unpredictability. Interstellar signals rarely fit neatly into our boxes. They challenge our assumptions, forcing scientists to stay humble and adaptable. The WOW signal's enduring puzzle reminds us that sometimes the cosmos's greatest gifts aren't answers, but questions that push us to look deeper, listen harder, and keep wondering what else might be out there. Now, let's turn our attention to another cosmic whisper that rewrote the rules: the Lorimer burst. Back in 2007, astronomer Duncan Lorimer and his team stumbled upon something extraordinary while sifting through old radio telescope data. A single, blisteringly intense burst of radio waves lasting just a few milliseconds had flashed across the universe, but here's what made it jaw-dropping. It packed as much energy as the Sun releases in 30,000 years. And then, just like that, it vanished without a trace. This wasn't just another blip in the cosmic static. The Oumuamua burst was the first documented fast radio burst, or FRB, a phenomenon so fleeting and powerful it left scientists scrambling for explanations. Pinpointing its origin was like trying to find a needle in a galaxy-sized haystack. The burst's dispersion, how its waves stretched out as they traveled through space, suggested it came from billions of light-years away, far beyond our Milky Way. But without a repeat signal or a visible source, the mystery only deepened. What the Oumuamua burst did, though, was crack open an entirely new window into astrophysics. Before this, no one knew such ultra-brief, ultra-energetic signals even existed. Suddenly, astronomers had a new cosmic puzzle to solve. What could possibly unleash such a staggering amount of energy in mere milliseconds? Theories ranged from colliding neutron stars to evaporating black holes, even speculative ideas about advanced alien technology. But one thing was clear: the universe had just handed us a new kind of enigma, one that would push our telescopes, our theories, and our imaginations to their limits. This discovery didn't just add to the catalogue of space mysteries, it created a whole new field of study. Today, FRBs are one of astronomy's hottest topics, with hundreds detected, and each one teaching us something new about the cosmos's hidden dramas. And it all started with that one inexplicable burst, a reminder that sometimes the universe's most profound secrets announce themselves in the blink of an eye. But the story of fast radio bursts doesn't end with that first jaw-dropping discovery. Fast forward to today, and these cosmic flashes have become one of space's most tantalizing riddles. What makes them even more puzzling? Their sheer unpredictability. Most FRBs are one-off events, here 1 millisecond, gone the next, leaving astronomers racing to catch them in the act. But then came the game changers, repeating FRBs. Unlike their one-time counterparts, these signals burst again and again from the same patch of sky, giving scientists rare clues to work with. One of the most famous repeaters, FRB121102, was traced back to a tiny, turbulent galaxy 3 billion light-years away. This wasn't just a lucky break, it was a roadmap. By studying repeaters, researchers noticed patterns. Some bursts flicker like a cosmic strobe light, while others spit out weaker echoes after the main blast. These quirks hint at extreme environments, like the violent neighborhoods of magnetars, supermagnetic neutron stars born from collapsing supernovas. Imagine a stellar corpse so dense, a teaspoon of it would weigh 1 billion tons, spinning wildly and snapping its magnetic fields like cosmic whips. That kind of energy could explain some FRBs, but not all bursts fit neatly into the magnetar theory. Some seem too powerful, too clean, sparking wilder ideas, like alien megastructures beaming energy across galaxies. While that's a long shot, it's a reminder of how little we truly understand. Even stranger are the local FRBs detected inside our own galaxy, which turned out to be magnetars throwing tantrums, proof that at least some bursts have natural origins. Here's why this all matters. Every new FRB is a breadcrumb in the cosmic forest. Repeaters help us map the universe's hidden matter by how their signals scatter. One-off bursts might mark cataclysmic events, like neutron stars colliding or black holes swallowing stars. And the more we listen, the weirder it gets, like FRBs that arrive with a side of X-rays or ones that pulse with clockwork precision. The bottom line, fast radio bursts are more than just space static. They're messengers from the universe's most chaotic corners, carrying secrets about magnetic fields, dark matter, and even the fabric of spacetime itself. And with every new detection, we're one step closer to decoding their cryptic language or stumbling upon something even more extraordinary. Now, let's shift our gaze to a signal that had the world holding its breath, the BLC1 controversy. In 2020, astronomers detected a mysterious radio signal seemingly coming from Proxima Centauri, the closest star system to our own. What made this discovery electrifying? For the first time in decades, a signal appeared to tick all the boxes of an artificial transmission narrowband, drifting in frequency just the way we'd expect from a technological source. The excitement was palpable. Could this finally be the long-awaited hello from our cosmic neighbors? But science thrives on skepticism, and the initial hype soon met reality. After months of painstaking analysis, researchers uncovered the truth. BLC1 wasn't an alien broadcast. Instead, it was likely human-made interference, a rogue signal mimicking the very characteristics we associate with extraterrestrial technology. The culprit, probably a distant satellite or even a malfunctioning device here on Earth. This revelation wasn't just a letdown, it was a masterclass in the challenges of hunting for alien signals. Here's why BLC1 matters beyond the disappointment. First, it exposed how easily human technology can muddy the waters. Our planet is drowning in radio noise, Wi-Fi, satellites, cell towers, all of which can masquerade as something otherworldly. Second, it highlighted the rigorous process of elimination scientists must follow. Every potential signal undergoes brutal scrutiny, from checking for repeatability to ruling out every conceivable natural or human origin. BLC1 passed some tests but crumbled under deeper inspection. Yet there's a silver lining. False alarms like BLC1 sharpen our methods. Each near miss teaches us to fine-tune our instruments and refine our criteria. They also remind us that the universe is vast, and the search for extraterrestrial intelligence is a marathon, not a sprint. So while BLC1 wasn't the breakthrough we hoped for, it's a stepping stone, a reminder that the next signal could be the real deal, hiding in plain sight, waiting for us to listen just a little more carefully. Now, let's take a closer look at what false positives like BLC1 teach us about the search for extraterrestrial intelligence. These near misses aren't just dead ends, they're invaluable lessons wrapped in cosmic intrigue. Every time a signal gets flagged as potential alien contact, only to be debunked, it forces scientists to tighten their methods and question their assumptions. One of the biggest takeaways: verification is everything. In the world of SETI, a single detection isn't enough. Signals must be repeatable, traceable, and scrutinized from every angle. BLC1, for instance, initially seemed promising because it matched certain artificial signatures, but it couldn't be replicated, a red flag that sent researchers digging deeper. This process of elimination is tedious but essential. It's like sifting through a mountain of static to find a whisper that stands out not just once but consistently. False alarms also reveal how sneaky human-made interference can be. Our planet is a cacophony of radio waves, from satellites to household electronics, all capable of mimicking the very signals we're hunting. BLC1 downfall was a reminder that we're often listening through layers of our own noise. But here's the twist: each false positive helps scientists build better filters. They learn to distinguish between Earth's chatter and the rare, tantalizing signals that might truly come from beyond. And let's not forget the excitement these near discoveries generate. Even when they fizzle out, they reignite public curiosity and remind us why the search matters. BLC1 didn't just make headlines, it sparked conversations about what real contact might look like and how we'd respond. That's the paradox of false positives. They're disappointments, yes, but they also keep the dream alive, pushing scientists and enthusiasts alike to keep listening, keep questioning, and stay ready for the day when the signal we've been waiting for finally breaks through the noise. So while BLC1 wasn't the message from the stars we hoped for, it sharpened our tools and sharpened our focus. The next time a strange signal emerges, we'll be even better prepared to separate the cosmic wheat from the terrestrial chaff. And who knows, the real deal might be just one careful analysis away. Now, shifting our gaze to another cosmic mystery, let's unravel the story of SHGb02+14a a signal that still baffles researchers 2 decades after its discovery. Detected back in 2003 by the SETI-at-Home project, this anomaly stood out not just for its unusual frequency, but for something even stranger, its erratic drift. Unlike most cosmic signals which maintain a steady frequency, SHGb02+14a wobbled unpredictably, as if the source itself were moving in ways we couldn't easily explain. What makes this signal so intriguing is its frequency range around 1420 MHz, a sweet spot often associated with hydrogen, the most abundant element in the universe. Scientists have long speculated that advanced civilizations might use hydrogen's natural frequency as a cosmic beacon, a sort of interstellar hello. But here's the twist: the signal's drift rate didn't match any known natural phenomenon. Planets, pulsars, and even distant galaxies have predictable movement patterns, but SHGb02+14a seemed to dance to its own rhythm. Theories about its origin range from the tantalizing to the technical. Some suggest it could be artificial, perhaps a transmitter on a fast-moving spacecraft or a planet with extreme atmospheric turbulence. Others argue it might be an artifact of human interference, though no earthly source has ever been pinned down. And then there's the location. The signal appeared to originate from a point between the constellations Pisces and Aries, where no notable stars or exoplanets had been identified at the time. Despite multiple attempts to reobserve it, SHGb02+14a vanished as mysteriously as it appeared, leaving astronomers with more questions than answers. Was it a fleeting glitch, a cosmic mirage, or something far more deliberate? The signal's elusiveness only deepens the enigma, cementing its place as one of the most compelling and frustrating candidates in the search for extraterrestrial intelligence. What sets SHGb02+14a apart is how it challenges our assumptions. If it was artificial, why hasn't it repeated? If natural, why doesn't it fit any known model? This anomaly reminds us that the universe is full of surprises, and sometimes the most puzzling signals are the ones that teach us the most about how much we still have to learn. Now let's dig deeper into the heart of the mystery, the strange frequency drift of SHGb02+14a. This isn't just a minor wobble in the data. It's a head-scratcher that forces scientists to rethink how signals from space should behave. Normally, when a signal drifts, it's because of something predictable like a planet's rotation or a star's motion. But this one, it zigged when it should have zagged, defying every textbook explanation. The big question is whether this drift points to a natural or artificial source. On the natural side, some have proposed extreme stellar phenomena, like a hyper-fast neutron star or a black hole's gravitational pull warping the signal's path. But here's the problem: none of these fully account for the signal's erratic behavior. It's like trying to fit a square peg into a round hole, close but not quite. Then there's the artificial angle. Imagine a transmitter on a spacecraft accelerating rapidly, causing the signal to shift unpredictably as it moves. Or maybe an alien civilization deliberately encoding information in the drift itself, turning what we see as chaos into a message. It's a thrilling idea, but without a repeat signal or more data, it's impossible to prove. What makes SHGb02+14a so frustrating and fascinating is how it sits right on the edge of our understanding. It's not clearly natural, but it's not clearly artificial either. This gray zone is where the most exciting discoveries often lurk, pushing scientists to develop new tools and theories. One thing's certain: signals like this remind us that the universe loves to keep us guessing. Every anomaly is a puzzle waiting to be solved, and SHGb02+14a. It's one of the most tantalizing puzzles of all. Now, shifting our gaze to another cosmic whisper, let's unravel the story of the HD 164,595 signal. Detected in 2015, this brief but intense burst of radio waves came from a star strikingly similar to our own Sun, located roughly 95 light-years away. For a moment, it sparked a whirlwind of excitement. Could this be the elusive hint of extraterrestrial intelligence we've been searching for? The signal stood out for its sheer power. If it was artificial, the energy required to produce it would have been staggering, on par with the entire output of a civilization harnessing their star's energy. That alone sent imaginations racing, but as quickly as the excitement flared, skepticism followed. Scientists scrambled to rule out more mundane explanations like interference from Earth-based sources. And sure enough, the culprit turned out to be far less exotic, a passing military satellite or perhaps even a glitch in the observing equipment. What's fascinating here isn't just the signal itself, but how the world reacted to it. The public's imagination latched onto the possibility of alien contact, while the scientific community remained cautiously analytical. This tension between hope and rigor is a recurring theme in the search for extraterrestrial signals. Every blip on the radar gets scrutinized, not just for what it could be, but for what it's most likely to be. HD 164,595 also highlights a critical lesson. The universe is full of natural and human-made noise, and teasing out a genuine signal from the chaos is painstaking work. Even false alarms like this one push researchers to refine their methods, ensuring that when, or if we do detect something truly extraordinary, we'll be ready to recognize it. So while this signal didn't rewrite the textbooks, it did remind us why we keep listening. The next cosmic hello could be just one frequency away. Now, let's turn our attention to a signal that had astronomers scratching their heads back in 2017, the mysterious whispers from Ross 128. This red dwarf star, just 11 light-years away, suddenly started sending out radio signals that didn't match anything we'd seen before. The patterns were strange, almost rhythmic, and for a brief moment, it felt like we might be onto something extraordinary. What made this signal so intriguing was its behavior. Unlike the usual cosmic static, it seemed to drift in frequency, almost as if it was trying to tell us something. Researchers at the Arecibo Observatory, the same team that had picked up the WOW signal decades earlier, were the ones to catch it, and just like before, the internet erupted with speculation. Could this be a message from an alien civilization orbiting Ross 128? But science thrives on skepticism, and the hunt for answers began. After months of careful analysis, the culprit turned out to be something far closer to home: satellite interference. Specifically, signals from geostationary satellites bouncing off the star's position in the sky had created the illusion of an extraterrestrial broadcast. It was a classic case of cosmic misdirection, a reminder that even our own technology can muddy the waters when we're searching for signs of life beyond Earth. Yet, Ross 128 mystery wasn't just a dead end. It taught us something crucial about exoplanet research. Red dwarfs like Ross 128 are prime targets in the hunt for habitable worlds. They're small, dim, and incredibly common in our galaxy. But their quiet nature also makes them prone to misinterpretation. A flicker of radio noise here, a blip of interference there, and suddenly we're chasing ghosts. This episode reinforced the need for extreme caution, for multiple lines of verification before jumping to conclusions. And while the signal itself was debunked, the star hasn't lost its allure. Ross 128 still holds potential. It's known to host at least one exoplanet, and who knows what else might be hiding in its orbit. The takeaway here isn't disappointment, it's patience. Every false alarm sharpens our tools, refines our methods, and brings us one step closer to the day when we might finally hear a signal that changes everything. Shifting our gaze from radio signals to something equally baffling, let's talk about Tabby's star, a cosmic oddity that had everyone from astronomers to sci-fi fans buzzing. Officially known as KIC 8462852, this star, located roughly 1,400 light-years away, didn't just flicker like most stars. It dimmed in ways that defied all expectations, dropping in brightness by up to 22% at times. That's not just unusual, it's downright unprecedented. What made Tabby's star stand out wasn't just the dimming itself, but the irregularity of it. Most stars dim predictably, maybe due to a planet passing in front or natural stellar activity. But the dips were chaotic, asymmetrical, and far too dramatic to chalk up to ordinary explanations. Cue the wild theories, the most headline-grabbing one. Alien megastructures. The idea was that an advanced civilization might have built a Dyson swarm, a massive array of solar collectors around the star, blocking its light in strange patterns. For a moment, it felt like science fiction might be crossing into reality. But as with all great cosmic mysteries, the truth turned out to be more nuanced. Further observations revealed that the dimming was likely caused by clouds of dust, not alien engineering. The dust particles were unevenly distributed, creating those bizarre, unpredictable dips in brightness. Still, the dust itself raised questions. Why was there so much of it? Why wasn't it behaving like typical interstellar dust? Tabby's star became a case study in how even the most tantalizing cosmic clues can lead us down unexpected paths. What's fascinating here is the parallel to unexplained radio signals. Just like the Ross 128 false alarm, Tabby's star taught us the importance of ruling out the mundane before leaping to the extraordinary. Yet, it also highlighted how these anomalies push science forward. The hunt for answers led to new methods of studying starlight, better tools for detecting exoplanets, and even fresh ideas about how alien civilizations might or might not reveal themselves. So while Tabby's star didn't give us aliens, it gave us something almost as valuable, a reminder that the universe is full of surprises, and sometimes the weirdest phenomena are the ones that teach us the most. And who knows, the next time a star dims unpredictably, we might just be ready to spot something truly groundbreaking. Now, let's turn our attention to a groundbreaking discovery that's reshaping our understanding of fast radio bursts, the chime repeater signals. Unlike the one-off bursts we've seen before, these repeating signals detected by the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have opened a whole new chapter in cosmic mysteries. What makes these FRBs so extraordinary is their consistency. Most fast radio bursts flash once and vanish, leaving scientists scrambling to trace their origins. But the chime repeaters, they come back, often from the same patch of sky, like a cosmic beacon with a message we're still trying to decode. The first of these repeating bursts, known as FRB 180916, was localized to a spiral galaxy about 500 million light-years away, a relatively close neighbor by cosmic standards. The fact that these bursts repeat throws a wrench into many existing theories. If FRBs were caused by cataclysmic events like neutron star collisions or black hole eruptions, they shouldn't happen more than once. Yet here we are with signals that defy that logic. One leading explanation points to Magnetar's highly magnetized neutron stars with eruptions powerful enough to produce these bursts. But even that doesn't fully explain the repeating patterns or why some FRBs are one-offs while others recur. What's even more intriguing is how chime discoveries have forced astronomers to rethink their tools. Traditional telescopes weren't designed to catch these fleeting, unpredictable signals. Chime, with its wide field of view and ability to scan large swaths of sky continuously, has become a game-changer, spotting dozens of new FRBs, including the elusive repeaters. These repeating bursts aren't just curiosities, they're clues. By studying their frequencies, polarizations, and host galaxies, scientists are piecing together a puzzle that could reveal everything from the nature of extreme cosmic environments to the structure of the universe itself. And while we're still far from definitive answers, one thing's clear. The chime repeaters have turned fast radio bursts from a cosmic oddity into a frontier of modern astrophysics. So, as we move forward, keep this in mind sometimes. The universe's most profound secrets aren't hidden in single, dramatic events, but in the patterns that repeat, waiting for us to listen closely enough. Now, shifting our gaze to another cosmic puzzle, let's unpack the Rattan 600 anomaly, a signal that had astronomers scratching their heads back in 2020. Detected by Russia's Rattan 600 radio telescope, this mysterious emission appeared to originate from the direction of HD 164595, a Sun-like star already under scrutiny for a previous signal in 2015. What made this detection so baffling was its ambiguity. Unlike the sharp, distinct bursts we see with fast radio bursts, the Rattan 600 signal was a steady, narrow-band emission, more like a faint, persistent hum than a sudden cosmic shout. Narrow-band signals are particularly intriguing because they're often associated with artificial sources, like human-made satellites or, hypothetically, extraterrestrial technology. But here's the twist. Follow-up observations failed to detect the signal again, leaving scientists without enough data to confirm its origin or even its exact location. The star HD 164595 added another layer of intrigue. Located roughly 94 light-years away, it's known to host at least one Neptune-sized planet, making it a plausible candidate for hosting life or at least sparking curiosity. But without a repeat signal, the Rattan 600 anomaly slipped into the realm of unresolved mysteries. Was it a glitch in the telescope's instrumentation, a passing satellite's radio interference, or something far more extraordinary? This case highlights a recurring challenge in the search for extraterrestrial signals. The line between groundbreaking discovery and false alarm is razor-thin. Without reproducibility, even the most tantalizing detections fade into uncertainty. Yet, the Rattan 600 anomaly reminds us that the cosmos is full of whispers we're still learning to interpret, each one a potential key to unlocking the universe's secrets. As we move forward, keep in mind that sometimes the most profound questions aren't answered with a bang, but with a silence that leaves us wondering what we might have missed. Turning our attention to another celestial enigma, let's revisit the curious case of the Andromeda signal, a fleeting whisper from our neighboring galaxy that sparked excitement and skepticism in equal measure. Back in 2015, researchers analyzing data from the Russian Academy of Sciences reported a peculiar radio emission seemingly originating from the Andromeda galaxy, the closest spiral galaxy to our Milky Way. At first glance, the signal had all the hallmarks of something extraordinary. It appeared as a narrow-band transmission, a type of signal often associated with artificial sources, much like the Rattan 600 anomaly we just discussed. Given Andromeda's staggering distance of 2.5 million light-years, the idea of detecting an artificial signal from there would have been groundbreaking if it held up. But almost as quickly as the news surfaced, it was met with skepticism. Follow-up observations by other telescopes failed to detect any trace of the signal, and astronomers soon concluded it was likely interference from earthly sources, possibly even a passing satellite. What makes the Andromeda signal so instructive is how it underscores the rigorous process of verifying interstellar detections. In the hunt for cosmic mysteries, false alarms are far more common than eureka moments. Every potential signal must pass a gauntlet of tests. Is it repeatable? Can it be pinpointed to a specific location? Does it match known natural phenomena? In this case, the answers were all no. Yet, the episode wasn't a failure, it was a masterclass in scientific caution. The Andromeda signal also highlights an ironic truth about our search for extraterrestrial intelligence. The more sensitive our telescopes become, the more they pick up human-made noise, from satellites to microwave ovens. Distinguishing cosmic whispers from terrestrial chatter is a growing challenge, one that requires ever more sophisticated methods. So while the Andromeda signal didn't rewrite the textbooks, it reinforced a vital lesson. In astronomy, patience and precision are just as important as discovery. The next time a strange signal emerges from the depths of space, scientists will be ready not just to listen but to question. Now, let's shift our gaze to a different corner of the cosmos, where the Kepler Space Telescope has uncovered its own share of mysteries. Among its many discoveries, one of the most puzzling has been the unexplained radio emissions detected near some of the exoplanets it observed. These signals, often faint but persistent, have left scientists scratching their heads, and astrobiologists particularly intrigued. What makes these Kepler radio signals so fascinating is their potential connection to magnetic fields. On Earth, our planet's magnetic field acts like a shield, deflecting harmful solar radiation and creating phenomena like the auroras. Some researchers speculate that the signals near these distant exoplanets could be evidence of similar magnetic activity, perhaps even hints of protective fields around potentially habitable worlds. If that's the case, it could mean these planets have the right conditions to support life as we know it. But here's the twist: not all of these signals fit neatly into existing models. Some appear too erratic, pulsing in ways that don't align with known natural processes. Could they be the result of unseen cosmic interactions, like charged particles colliding in a planet's atmosphere? Or might they point to something even more unexpected, like interactions between a planet and its host star? The possibilities are as vast as the Kepler mission's catalogue of exoplanets itself. For astrobiologists, these signals are like cosmic breadcrumbs. If a planet has a strong magnetic field, it's more likely to retain an atmosphere, a key ingredient for life. Detecting radio emissions could be one way to identify such worlds from afar, giving us clues about where to focus our search for life beyond Earth. Yet, as with so many interstellar mysteries, the Kepler signals remind us that the universe loves to keep us guessing. Every new detection raises as many questions as it answers, pushing the boundaries of what we thought possible. So while we may not yet have definitive answers, these enigmatic radio waves near Kepler's exoplanets are a thrilling piece of the puzzle. They remind us that even in the data of a retired telescope, the cosmos still has secrets waiting to be uncovered. Now, let's take a detour from deep space to a discovery that proves sometimes the universe's greatest mysteries are hiding right in our own backyard, or more accurately, in the break room. The Parkes Observatory in Australia, a powerhouse in radio astronomy, picked up a series of bizarre signals in the early 2000s that had scientists buzzing. These bursts, nicknamed puritans after a mythical stag-bird hybrid, seemed to defy explanation at first. They had all the hallmarks of something extraterrestrial: short, intense, and appearing to come from deep space. But here's where the story takes a hilarious turn. After years of head-scratching and ruling out cosmic sources, researchers traced the signals back to something far more mundane: microwave ovens. Specifically, the bursts occurred when observatory staff impatiently opened the microwave doors before the timer finished. The sudden release of trapped radio waves mimicked the kind of distant, mysterious signals astronomers spend their careers hunting. It was a classic case of cosmic comedy, proof that even the most advanced science can be tripped up by everyday human quirks. What makes the Puritan saga so delightful isn't just the punchline, though. It's a brilliant reminder of how careful scientists have to be when interpreting data. These signals passed initial scrutiny because they were so convincing, highlighting the challenges of distinguishing between true cosmic phenomena and terrestrial interference. The discovery also led to tighter protocols at observatories worldwide, ensuring microwave-related mysteries wouldn't muddy the waters again. Yet, there's a deeper lesson here too. The Puritans show how science self-corrects, how patience and skepticism eventually untangle even the most perplexing anomalies. And let's be honest, there's something wonderfully human about the fact that our search for alien signals once got sidetracked by someone's reheated lunch. So while the Puritans may not rewrite our understanding of the cosmos, they've certainly earned their place as one of astronomy's most endearing blunders. A cosmic whodunit solved not with telescopes, but with a little humility and a lot of laughter. Shifting our gaze from microwave mishaps to the depths of the cosmos, let's unravel the enigma of Glimpse C01, a signal that emerged from one of the most crowded neighborhoods in our galaxy. Nestled within a dense star cluster roughly 10,000 light-years away, this mysterious radio emission has left astronomers scratching their heads. Unlike the Puritans, there's no earthly explanation here, just a cosmic puzzle wrapped in the chaos of a stellar crowd. What makes Glimpse C01 so intriguing is its origin. Star clusters like this one are bustling with activity, packed with stars orbiting each other in a gravitational dance. Normally, radio signals from such regions are predictable pulsars spinning like lighthouses or the hum of gas clouds. But Glimpse C01 doesn't fit the mold. It's erratic, flickering in ways that defy conventional astrophysics. Some theories suggest it could be a rare type of magnetar, a neutron star with an unimaginably strong magnetic field. Others wonder if it's evidence of something even more exotic, like a black hole devouring a nearby star in slow motion. Studying signals like this is like trying to eavesdrop on a conversation in a packed stadium. The sheer density of stars creates a cacophony of background noise, making it incredibly hard to isolate individual sources. Add to that the distortion caused by interstellar gas, and you've got a recipe for frustration. Yet, it's precisely these challenges that make Glimpse C01 so valuable. Every flicker and burst forces scientists to refine their tools and techniques, pushing the limits of what our telescopes can discern. One of the biggest hurdles is distance. 10,000 light-years means we're seeing this cluster as it was when humans were first mastering agriculture. The light reaching us today has traveled across millennia, carrying whispers of events long past. By the time we detect a signal, the object that produced it might have already vanished, collapsed into a black hole, or torn apart by tidal forces. It's a humbling reminder of how time and space stretch our understanding of the universe. So why keep searching? Because hidden in these chaotic stellar cities could be clues to some of astronomy's biggest questions. How do stars interact in such extreme environments? What rare cosmic phenomena might be lurking in the noise? Glimpse C01 isn't just a mystery, it's a beacon, drawing us deeper into the wild, untamed heart of our galaxy. And who knows, the next signal we decode might rewrite the textbooks. Now, let's rewind the cosmic clock to one of the most amusing yet groundbreaking mix-ups in astronomy, the story of the LGM pulsar. Back in 1967, a young researcher named Jocelyn Bell Burnell was scanning the skies when she stumbled upon a signal so precise, so rhythmic, it seemed almost artificial. Pulses arrived every 1.337 seconds with clockwork regularity, sparking whispers of an unthinkable possibility. Could this be a message from extraterrestrials? The team even jokingly labeled it LGM1, short for Little Green Men. But the truth turned out to be far more fascinating than science fiction. What Bell Burnell had discovered wasn't an alien broadcast, but nature's own lighthouse, a pulsar. These incredibly dense neutron stars, remnants of supernova explosions, spin at mind-bending speeds, beaming radiation across the cosmos like a cosmic strobe light. The precision of their pulses comes from their rotation, not intelligence. Yet for a brief, thrilling moment, humanity caught a glimpse of how easy it is to mistake the universe's natural wonders for something beyond our understanding. This misinterpretation wasn't just a funny footnote, it revolutionized astronomy. Pulsars became cosmic tools, helping scientists test Einstein's theory of relativity, map the galaxy's magnetic fields, and even hunt for gravitational waves. The LGM episode also taught astronomers a vital lesson. Extraordinary claims require extraordinary evidence. It set the gold standard for skepticism in the search for extraterrestrial signals, ensuring that today, when we detect something unusual, we rule out every natural explanation before jumping to otherworldly conclusions. What's remarkable is how pulsars, once mistaken for alien hails, now serve as some of the universe's most reliable signposts. Their steady ticks are so predictable that researchers have proposed using them as interstellar GPS for future space travel. From a false alarm to a cornerstone of astrophysics, the LGM story reminds us that sometimes the universe's greatest gifts come wrapped in mystery and a dash of humor. Now, shifting our gaze from mysterious signals to an enigmatic visitor, let's talk about Oumuamua, the first known interstellar object to pass through our solar system. Discovered in 2017, this strange, elongated body defied all expectations. Unlike typical comets or asteroids, Oumuamua lacked a visible tail of gas and dust, yet it accelerated as it moved away from the Sun, as if pushed by an unseen force. This bizarre behavior sent shockwaves through the scientific community. Some researchers, including Harvard astronomer Avi Loeb, floated the idea that Oumuamua might not be a natural object at all. Could it be a piece of alien technology, perhaps a solar sail or a derelict probe? The speculation wasn't entirely baseless. The object's unusual shape, estimated to be up to 10 times longer than it was wide, and its unexpected acceleration made it unlike anything we'd seen before. But as with the LGM pulsar, the truth turned out to be more nuanced. Further analysis suggested that Oumuamua's acceleration might have been caused by outgassing, a release of trapped gases that acted like a natural thruster. Without a visible tail, this explanation left room for doubt, but it highlighted how little we understand about interstellar objects. The controversy taught astronomers a crucial lesson. The universe is full of surprises, and sometimes the most extraordinary explanations aren't the right ones. Oumuamua's fleeting visit left us with more questions than answers, but it also sharpened our tools for future detections. Now, telescopes like the Vera-C Rubin Observatory are poised to spot more of these interstellar travelers, helping us distinguish between natural oddities and potential signs of intelligence. Whether it was a cosmic iceberg or something even stranger, Oumuamua reminded us that the line between mystery and discovery is often thinner than we think. Now, let's turn our attention to a burst that lit up the cosmos with unprecedented intensity, the Tarawera burst. Discovered in 2020, this fast radio burst, or FRB, wasn't just another blip in the data. It was one of the brightest ever recorded, packing more energy in a millisecond than our Sun emits in days. What made Tarawera truly groundbreaking, though, was its pinpointed origin. For the first time, astronomers traced an FRB not just to a general region of space, but to a specific galaxy, a spiral galaxy much like our own Milky Way, located roughly 3.6 billion light-years away. This localization was a game-changer. By studying the host galaxy's environment, scientists uncovered clues about what might trigger these colossal bursts. Unlike earlier FRBs linked to chaotic, star-forming regions, Tarawera home galaxy was relatively calm, suggesting these explosions don't always require extreme conditions. Some theories point to Magneta's highly magnetic neutron stars as the culprits, while others speculate about collisions between dense objects like black holes or neutron stars. But Tarawera brightness added another twist. It was so powerful that it challenged existing models of how FRBs are produced. The burst also left behind a faint, lingering radio glow, a rare feature that gave researchers a longer window to study its aftermath. This afterglow hinted at complex processes at work, like shockwaves plowing through interstellar gas or a magneta's turbulent magnetic field. While Tarawera didn't solve the FRB mystery outright, it narrowed the possibilities, showing that these signals can emerge from diverse cosmic neighborhoods. As telescopes grow more sensitive, each new FRB discovery, like Tarawera, brings us closer to unraveling their secrets. Whether they're cosmic accidents or the signatures of unseen astrophysical phenomena, one thing is clear: these bursts are rewriting the rules of how we understand the universe's most energetic events. Shifting our gaze from the brilliance of fast radio bursts, we now encounter a mystery that tugs at the very fabric of the cosmos, the eerie phenomenon known as the dark flow. Unlike anything else we've explored, this anomaly isn't about signals from distant galaxies, but rather a strange, large-scale motion hidden within the cosmic microwave background, the afterglow of the Big Bang itself. In 2008, astronomers studying this ancient light noticed something unsettling. Galaxy clusters' massive structures bound by gravity seemed to be drifting in the same direction at staggering speeds, as if pulled by an invisible force. This motion, dubbed the dark flow, suggested the presence of something colossal beyond the edges of our observable universe, a gravitational influence so vast it defied conventional cosmology. The implications were profound. If real, the dark flow hinted at structures or even other universes lying far beyond what our telescopes can see, tugging on the matter we know like a cosmic undertow. Skeptics, however, argued it could be a statistical fluke or an artifact of incomplete data. Some proposed that uneven heating in the early universe might mimic the effect, while others doubled down on the idea of undiscovered physics. What makes this enigma so tantalizing is its scale. The dark flow isn't just a local oddity, it spans billions of light years, challenging our understanding of the universe's uniformity. Could it be evidence of a multiverse or simply a quirk in our measurements? The debate rages on, with newer studies both supporting and contradicting the original findings. As we push the boundaries of observation, the dark flow remains one of cosmology's most provocative puzzles. Whether it reveals unseen realms or forces us to rethink our models, it's a stark reminder that the universe still holds secrets we've only begun to glimpse. Now, let's turn our attention closer to home, or at least closer to the heart of our own galaxy. Rising like colossal, ghostly towers above the Milky Way's bustling center, the Fermi bubbles are one of the most striking cosmic mysteries lurking right in our galactic backyard. Discovered in 2010 by NASA, a Fermi Gamma-ray space telescope, these enormous structures stretch an astonishing 25,000 light-years above and below the galactic plane, glowing with high-energy gamma rays. What makes these bubbles so baffling is their sheer energy and the fact that they don't fit neatly into any existing model of galactic behavior. Scientists have proposed several theories to explain their origin, but none fully account for their scale or intensity. One leading idea suggests they're the aftermath of a past feeding frenzy by the supermassive black hole at our galaxy's core, Sagittarius, a star. If true, this would mean the black hole devoured an enormous amount of material millions of years ago, releasing jets of energy that inflated these bubbles like cosmic balloons. Another possibility points to a burst of star formation in the galactic center, where waves of exploding stars could have pumped energy into the surrounding gas. Yet, even this dramatic explanation struggles to match the bubble's precise structure and longevity. What's even more intriguing is that the edges of the Fermi bubbles are unusually sharp, as if they're being held in place by some invisible force, a feature that defies expectations of how such energetic phenomena should behave. Adding to the puzzle, the bubbles emit not just gamma rays but also X-rays and radio waves, hinting at a complex interplay of particles and magnetic fields. Some researchers have even speculated about more exotic origins, like dark matter annihilation, though evidence for this remains elusive. The Fermi bubbles remind us that even our own galaxy harbors enigmas we're still unraveling. Whether they are scars from a violent galactic event or signs of something entirely new, they challenge our understanding of how galaxies evolve and what might still be hidden in plain sight. Now, let's venture into the realm of cosmic oddities, where galaxies defy expectations in the most spectacular ways. Among these celestial curiosities are the so-called X-shaped radio galaxies, a rare breed of galactic structures that baffle astronomers with their striking symmetry and mysterious origins. These galaxies get their name from the dramatic X-shaped pattern of radio waves they emit, stretching far beyond their visible starlight. What makes them so unusual is that this shape doesn't align with the typical behavior of galaxies, where radio emissions usually form neat jets or lobes. Instead, these X-shaped structures suggest something far more chaotic and possibly violent has taken place. The leading theory points to galactic collisions. Imagine two galaxies, each with its own supermassive black hole, merging in a cosmic dance. As their black holes spiral toward each other, their jets of high-energy particles normally shooting in opposite directions could get twisted and reshaped by the gravitational turmoil, forming that distinctive X. It's like two whirlpools colliding, sending ripples in unexpected directions. But not all X-shaped galaxies fit this explanation. Some show no obvious signs of a recent merger, leaving scientists to wonder if other processes, like sudden shifts in a black hole's spin or even multiple outbursts of energy, could be at play. Adding to the intrigue, these galaxies are incredibly rare. Only a handful have been confirmed so far, making each discovery a precious clue in unraveling their secrets. What's clear is that X-shaped radio galaxies challenge our understanding of how black holes influence their surroundings. Whether they're cosmic crash sites or the result of hidden galactic upheavals, they remind us that the universe still holds plenty of surprises even in the shapes we thought we knew. Now, shifting our gaze to one of the most colossal structures in the known universe, we encounter the Hercules Corona Borealis Great Wall. This mind-bending cosmic behemoth stretches across an astonishing 10 billion light-years, making it one of the largest single entities ever discovered. But what truly baffles astronomers isn't just its size. It's the strange, uneven distribution of gamma-ray bursts within it. Gamma-ray bursts, the most energetic explosions in the universe, typically occur randomly across the cosmos. Yet within this vast wall, they cluster in a way that defies our current understanding of cosmic structure. Imagine tossing a handful of glitter into the air and watching it gather in one specific corner instead of scattering evenly. That's the kind of oddity scientists are grappling with here. The leading theories suggest this clustering might trace back to the early universe, where dense regions of matter could have seeded these bursts. Some researchers propose that the wall's sheer scale hints at flaws in our cosmological models, particularly the principle that the universe should look roughly the same in all directions on large scales. If matter isn't as evenly distributed as we thought, it could force a rewrite of fundamental astrophysics. Adding to the mystery, the Hercules Corona Borealis Great Wall challenges the theoretical size limit for cosmic structures. According to current models, nothing this big should exist, yet there it is, looming in our data. Whether it's a statistical fluke or a sign of deeper cosmic rules we've yet to uncover, one thing is certain. This colossal wall and its enigmatic bursts are pushing the boundaries of what we know about the universe's architecture. As we ponder this cosmic giant, it's a humbling reminder that even our most advanced telescopes are only scratching the surface of the universe's grand design. Now, let's venture into the shadowy realms of the cosmos, where the very fabric of reality seems to play tricks on our instruments. Meet the dark galaxy hypothesis, a tantalizing idea that some of the radio signals we detect might be coming from galaxies we can't even see. These aren't just ordinary galaxies hiding behind cosmic dust. They're entire structures made almost entirely of dark matter, the mysterious substance that makes up roughly 85% of the universe's mass but refuses to interact with light. Imagine a galaxy where stars are few and far between, or perhaps absent altogether. Instead, it's a ghostly assemblage of dark matter, its presence betrayed only by the faint whispers of radio waves. Scientists first stumbled upon this possibility when they noticed strange, diffuse radio emissions that didn't align with any visible galaxies. The signals were too widespread and too uniform to come from known sources, sparking the question, could there be entire galaxies out there, invisible to our telescopes, yet massive enough to bend the fabric of space around them? The hunt for these dark galaxies is like trying to find a shadow in a pitch-black room. researchers use radio telescopes to map the subtle distortions in nearby gas clouds, looking for the gravitational fingerprints of unseen mass. Some candidates, like Dragonfly 44, have emerged galaxies with so few stars that their sheer weight can only be explained by enormous amounts of dark matter. But confirming their existence is a painstaking process, requiring cross-verification with multiple instruments and techniques. What makes this hypothesis so compelling is its potential to solve multiple cosmic puzzles at once. If dark galaxies exist, they could explain why some regions of space seem to have more gravity than visible matter can account for. They might also shed light on how dark matter behaves on galactic scales, offering clues to its true nature. Yet for now, these shadowy structures remain just beyond our grasp, teasing us with their elusive signals. As we peer deeper into the cosmic dark, one thing becomes clear: the universe still holds secrets that defy even our most advanced tools. And the search for dark galaxies is a reminder that sometimes the most profound discoveries begin with the faintest whispers in the void. Now, let's turn our attention to one of the largest known structures in the universe, the Sloan Great Wall. Stretching over 1 billion light-years across, this colossal filament of galaxies defies expectations, not just by its sheer size but by the strange signals it emits. These unexplained emissions ripple through the cosmic web, challenging one of astronomy's foundational ideas, the cosmological principle, which assumes the universe is uniform on the largest scales. The Sloan Great Wall isn't just a random clustering of galaxies. It's a titanic ribbon of matter, so vast that it shouldn't exist under our current models. Yet there it is, and what's even more puzzling are the anomalous radio waves emanating from its depths. These signals don't match the typical emissions from star-forming regions or supermassive black holes. Instead, they pulse with a rhythm that suggests something far more mysterious at work. Perhaps large-scale magnetic fields or even unknown physical processes woven into the fabric of the wall itself. What makes these emissions so controversial is their scale. If the universe is truly homogeneous, as the cosmological principle suggests, why would such a massive structure produce such concentrated, irregular signals? Some researchers argue that the Sloan Great Wall might be a rare statistical fluke, a cosmic accident in an otherwise uniform cosmos. Others propose more radical ideas, like flaws in our understanding of gravity or hidden dimensions influencing matter on scales we're only beginning to probe. The debate isn't just academic. If the anomalies in the Sloan Great Wall hold up under scrutiny, they could force us to rethink how matter organizes itself across the universe. Are we seeing the limits of the cosmological principle, or is there a deeper layer of cosmic structure waiting to be uncovered? For now, the Sloan Great Wall stands as both a marvel and a mystery, a reminder that even our grandest theories must bend before the universe's endless creativity. As we move forward, the next signal takes us from the vastness of galactic walls to the intimate chaos of colliding galaxies, where another enigma awaits. Now, let's step into the eerie realm of the ghost FRB fast radio bursts that seem to come from nowhere. Unlike other cosmic signals tied to galaxies or star clusters, these bursts arrive without any visible source, as if the universe itself is whispering secrets we can't quite trace. What makes these ghostly signals so baffling is their sheer isolation. When astronomers point their telescopes toward the origin of a typical fast radio burst, they usually find a host galaxy, a home for the explosion. But with ghost FRBs, there's nothing. No galaxy, no star, not even a wisp of interstellar gas to explain their existence. It's like hearing a knock at your door, only to open it and find empty space. The implications are staggering. If these bursts truly have no host, they could be traveling far longer distances than we thought, passing through uncharted regions of the cosmos. Some scientists speculate they might originate from rogue objects, nomadic neutron stars, or black holes flung out of their galaxies during violent collisions. Others wonder if they're the echoes of ancient cosmic events, their light stretched so thin over billions of years that their origins have literally faded from view. Tracking these phantoms requires next-level technology. Current telescopes simply aren't sensitive enough to pinpoint their exact origins, but upcoming instruments like the Square Kilometre Array could change that. By capturing these bursts in unprecedented detail, we might finally uncover whether they're drifting through intergalactic voids or hiding in galaxies too faint for us to see. One thing's certain, ghost FRBs challenge our understanding of where and how cosmic signals can form. Are they cosmic misfits, or do they hint at entirely new astrophysical phenomena? As we push the limits of our technology, these enigmatic bursts remind us that the universe still holds mysteries we've only begun to imagine. And speaking of cosmic mysteries, our next signal takes us into the heart of galaxy clusters, where faint, diffuse radio waves paint another puzzling picture of the universe's hidden workings. Now, shifting our gaze to the vast gatherings of galaxies, we encounter the enigmatic dragonfly radio source's faint, wispy signals that seem to flutter through the cosmos like their namesake. These elusive emissions are woven into the fabric of galaxy clusters, the universe's most massive structures where hundreds or even thousands of galaxies swarm together in a gravitational dance. What sets dragonfly signals apart is their ghostly, diffuse nature. Unlike the sharp bursts or focused jets we've seen elsewhere, these radio waves stretch across vast distances, forming delicate filaments that intertwine with the cluster's hot gas. Picture a spider's web glinting with dew, except this web is light years wide, and the dew is the faint glow of charged particles spiraling through magnetic fields. The leading theory, turbulence. Galaxy clusters are cosmic cauldrons of violence, where mergers and collisions send shockwaves rippling through the surrounding gas. These chaotic events could accelerate particles to near light speeds, causing them to emit radio waves as they twist and spiral. Another possibility involves relic radiation, echoes of ancient explosions or black hole activity that linger like cosmic fingerprints long after the original event has faded. But dragonfly sources aren't just relics, some appear linked to ongoing chaos. In clusters like Able 2255, astronomers see these radio tendrils aligned with weather fronts of gas, suggesting they're actively shaped by the cluster's stormy environment. It's as if the universe is painting with invisible ink, using magnetic fields and particle winds to sketch these ethereal structures. The challenge lies in their faintness. Detecting dragonfly emissions requires radio telescopes with exquisite sensitivity, like the low-frequency array LOFAR, which acts like a cosmic hearing aid, amplifying whispers from the depths of space. Even then, their origins remain debated. Could they trace the paths of dark matter, or are they markers of hidden black hole outbursts too diffuse to spot directly? One thing's clear, these delicate radio threads are more than cosmic decoration. They're clues to the forces that shape galaxy clusters, the same forces that, over billions of years, dictate where and how galaxies form. And as we refine our tools, we're learning to read their patterns, uncovering the invisible storms that rage between the stars. Up next, we'll encounter another radio riddle, this time in the form of vast, mysterious rings that defy even the wildest cosmic explanations. Now, let's turn our attention to one of the most baffling discoveries in recent radio astronomy, the odd radio circles, or ORC. These enormous, ring-shaped signals were first spotted in 2020, and they've left scientists scratching their heads ever since. Imagine looking up at the night sky and seeing perfect, ghostly halos of radio light, some so vast they could swallow entire galaxies. That's exactly what ORCs are, mysterious cosmic donuts with no clear explanation. What makes them so puzzling? For starters, they're invisible in optical, infrared, or X-ray light. They only show up in radio wavelengths, like whispers in a frequency only certain telescopes can hear. Their symmetry is another head-scratcher. Most cosmic structures are messy, think exploding stars or tangled galaxy collisions, but ORCs are eerily round, as if someone drew them with a compass. And they're not small. Some span hundreds of thousands of light years, dwarfing the galaxies they sometimes encircle. So, what could they be? One leading theory points to shockwaves from colossal explosions. Picture a supernova on steroids, a galactic-scale detonation, perhaps triggered by merging supermassive black holes. The blast would send a spherical wave of energy rippling outward, lighting up the surrounding gas like a neon sign. Another idea involves wormhole echoes. Some theorists suggest ORCs might be the mouths of wormholes, their extreme gravity bending radio waves into circular patterns. It's a wild idea, but in a universe full of surprises, why not? Then there's the starburst bubble hypothesis. Intense bursts of star formation can blow gigantic bubbles in interstellar gas, which might glow in radio waves. But ORCs are often far from star-forming regions, leaving this theory on shaky ground. And let's not forget the dark horse candidate, relics from an ancient universe-wide event, like a long-ago collision of parallel dimensions. Okay, that one's speculative, but that's the fun of ORCs. They defy easy answers. The hunt for clues is on. Telescopes like the Australian Square Kilometre Array Pathfinder ASCAP are scanning the skies for more ORCs, hoping to catch them in different stages or environments. Each new discovery could tip the scales toward one explanation, or send us back to the drawing board. One thing's certain, these cosmic rings are more than just curiosities. They're windows into the universe's most extreme physics, challenging us to rethink what's possible. Up next, we'll zoom in on a different kind of radio mystery, tiny but mighty galaxies pumping out signals that shouldn't make sense, yet somehow do. Now, shifting our gaze to something smaller but no less fascinating, let's dive into the blueberry starbursts. These aren't your average galaxies, they're tiny, compact powerhouses, bursting with star formation at rates that defy logic. Picture a galaxy no bigger than a fraction of our Milky Way, yet churning out stars hundreds of times faster. That's the magic of these so-called blueberries, and their radio emissions are just as intense as their nickname suggests. What makes them stand out in cosmic surveys? For one, their sheer energy. These galaxies are like cosmic fireworks, lighting up the radio spectrum with frenetic activity. Their compact size means all that star formation is crammed into a tight space, creating a pressure cooker of radiation and magnetic fields. This chaos generates radio waves so bright they punch far above their weight, making them easy to spot even across vast distances. But why the rapid star formation? One theory points to recent collisions or mergers. When small galaxies smash together, their gas clouds get compressed, igniting a frenzy of new stars. Another idea suggests they're relics from the early universe, pristine pockets of gas that never slowed down their star-making machinery. Either way, blueberries challenge our assumptions about how galaxies evolve. And here's the kicker, they're helping scientists understand the universe's missing radio sources. Surveys often detect faint, unexplained signals, and blueberries might be the culprits behind some of them. Their unique properties, small size, extreme activity, mean they can masquerade as other phenomena until closer inspection. As telescopes grow more sensitive, we're finding more of these cosmic berries, each one a clue to the turbulent lives of small galaxies. Up next, we'll explore another radio oddity, this time from galaxies so energetic they've earned the whimsical name green peas. Now, let's turn our attention to another cosmic curiosity, the green pea galaxies. These tiny, vibrant galaxies might sound playful, but their radio signals pack a serious punch. Unlike their fruity nickname suggests, green peas are anything but ordinary. They're small, yes, but they're also incredibly energetic, emitting radio bursts that stand out even in the crowded cosmic symphony. What makes green peas so special? For starters, their color. These galaxies glow with an intense green hue thanks to the light emitted by ionized oxygen, a telltale sign of furious star formation. But it's their radio emissions that really grab astronomers' attention. Unlike typical galaxies, green peas produce sporadic, high-energy radio bursts that don't quite fit the usual patterns. Some theories suggest these bursts come from supermassive black holes feeding at their cores, while others point to colossal stellar explosions or even magnetars ultra-dense, spinning neutron stars with unimaginably strong magnetic fields. Here's where it gets even more intriguing. Green peas might be cosmic time capsules. Many of them exist in the distant universe, meaning we're seeing them as they were billions of years ago. Their unusual radioactivity could be a snapshot of how young galaxies behaved during the universe's most chaotic eras. By studying them, scientists hope to unravel how galaxies transition from their fiery, star-forming youth to the more settled giants we see today. And there's a twist: some green peas show signs of leaking radiation. Their intense star formation can blow holes in their own gas clouds, allowing energy to escape in unpredictable ways. This could explain why their radio signals sometimes appear jumbled or fragmented, adding another layer to the mystery. As we piece together the story of these peculiar galaxies, one thing's clear: green peas are more than just a colorful oddity. They're a key to understanding how the universe's smallest galaxies can have the biggest impact on cosmic evolution. Next up, we'll venture into the symmetrical beauty of the Red Square Nebula, where radio emissions paint a picture as precise as it is puzzling. Shifting our gaze from the energetic chaos of green peas, we arrive at a cosmic masterpiece, the Red Square Nebula. This celestial structure isn't just a feast for the eyes. Its radio emissions are a symphony of precision, wrapped in a mystery that defies easy explanation. At first glance, the Red Square Nebula lives up to its name. Its near-perfect symmetry, with intersecting gas clouds forming an almost mathematical X-shape, makes it one of the most visually striking objects in space. But what truly captivates astronomers isn't just its beauty, it's the radio waves echoing from within. Unlike the erratic bursts of green peas, the red square's emissions are eerily consistent, pulsing with a rhythm that suggests an underlying order. So, what's creating these symmetrical signals? The leading theory points to a binary star system at the nebula's heart. As two stars orbit each other, their gravitational dance shapes the surrounding gas into that iconic X pattern, while their stellar winds excite the gas, causing it to emit radio waves. But here's the puzzle: the signals are too uniform. Natural processes usually introduce some chaos, yet the red square's emissions are as precise as a metronome. Some researchers wonder if magnetic fields, twisted by the star's motion, are acting like cosmic tuning forks, organizing the radio waves into such clean patterns. And then there's the nebula's echoes. These aren't literal sounds, of course, but repeating radio signatures that seem to bounce off the nebula's walls. Imagine shouting into a canyon and hearing your voice return, except here, the canyon is light years wide, and the voice is a star's energy reverberating through space. These echoes could hold clues about the nebula's density, temperature, and even its age, offering a rare chance to map its hidden structure. Yet for all its elegance, the red square resists full understanding. Why does its symmetry persist across multiple wavelengths? Could there be an unseen force, like a black hole or a dense dust disk, refining its shape? Or is this simply how some stars choose to announce their presence, with artistry as deliberate as it is enigmatic? As we marvel at this cosmic gem, remember, the red square isn't just a pretty face. It's a reminder that even in the vast, chaotic universe, nature sometimes drafts its blueprints with a ruler and leaves us to decode the measurements. Up next, we'll meet a pulsar whose signals are twisted by a companion star, proving that cosmic partnerships can be as disruptive as they are dazzling. Now, let's turn our attention to a cosmic partnership that's anything but harmonious: the Black Widow pulsar. This isn't your average stellar duo. Here, one star is literally consuming the other, and the signals we detect from this violent dance are twisted in ways that baffle even seasoned astronomers. At the heart of this system lies a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. But unlike solitary pulsars, this one has a companion, a smaller star locked in a deadly embrace. The pulsar's intense gravity and radiation are slowly stripping material from its partner, earning it the Black Widow nickname. As this stolen matter spirals toward the pulsar, it doesn't just vanish, it distorts the pulsar's radio signals, warping them into patterns unlike anything else in the cosmos. What makes these distortions so fascinating? For one, they're unpredictable. Most pulsars emit steady, rhythmic pulses, but the Black Widow's signals flicker and fade, as if someone's fiddling with a cosmic dimmer switch. This happens because the stolen gas forms a turbulent cloud around the pulsar, scattering and absorbing its radio waves. At times, the companion star even eclipses the pulsar entirely, blocking its signals for minutes or hours. It's like watching a lighthouse blink out behind a thick fog. Only here, the fog is a storm of superheated plasma. But the real puzzle is how these distortions reveal the system's extreme physics. By studying the signal disruptions, astronomers can map the companion star's atmosphere, measure its evaporation rate, and even glimpse the magnetic chaos near the pulsar's surface. Some theories suggest the pulsar's beams are being bent into bizarre shapes, like light passing through a funhouse mirror. Others propose that the companion star's own magnetic field is tangling with the pulsars, creating interference that scrambles the signals further. Yet for all its violence, the Black Widow system is also a cosmic clock, one that's slowly winding down. Over millions of years, the pulsar will consume its partner entirely, leaving behind a silent neutron star and a ghostly cloud of ionized gas. Until then, its distorted signals offer a front-row seat to one of the universe's most destructive relationships, a reminder that even in space, some bonds are anything but peaceful. Up next, we'll explore a ghostly intergalactic cloud with a radio voice of its own, proving that cosmic mysteries aren't always where we expect to find them. Now, let's shift our gaze to something truly otherworldly, a cosmic ghost story with a radio twist. Meet Hanny's Voorwerp, a bizarre, glowing cloud drifting through space like an interstellar spectre. Discovered in 2007 by a school teacher named Hanny van Arkel while she was classifying galaxies online, this eerie green blob quickly became one of astronomy's most captivating oddities. At first glance, it looks like a forgotten fragment of a galaxy, but here's the twist: it doesn't contain any stars. Instead, this cloud is a colossal mass of ionized gas, stretching tens of thousands of light years across, and it's singing to us in radio waves. The mystery: what's powering its glow and those faint but persistent radio whispers? The answer lies in a dramatic cosmic event from the distant past. Hanny's Voorwerp is linked to a nearby galaxy, IC249, which once hosted a ferociously active quasar at its core. Quasars are supermassive black holes that devour matter, blasting out enough energy to outshine entire galaxies. Scientists believe that millions of years ago, this quasar flicked on like a cosmic spotlight, flooding the surrounding space with intense radiation. The Voorwerp, floating just far enough away, got caught in the glare. The gas within it became ionized, charged with energy, and began to glow, a process we call light echo. But here's where it gets even stranger. By the time the quasar's light reached the Voorwerp, the quasar itself had already gone quiet. The black hole had either run out of fuel or was obscured by dust, leaving the Voorwerp as the only visible relic of its violent reign. It's like stumbling upon a still glowing ember long after the fire has died. The radio emissions add another layer to the puzzle. Unlike the optical glow, which comes from ionized gas, the radio signals suggest something more. Perhaps shockwaves from past quasar outbursts or even lingering magnetic activity in the cloud itself. Some researchers speculate that the VORWARP might still be reacting to the quasar's ancient energy, like ripples in a pond long after the stone was thrown. What makes Hani's VORWARP so special isn't just its ghostly appearance, it's a time capsule. By studying its radio whispers, astronomers can piece together the life cycle of quasars and the way they shape their surroundings long after they've faded. It's a reminder that even in the quiet corners of the universe, echoes of cosmic violence linger, waiting to be heard. Up next, we'll encounter a galaxy that defies expectations with its serene beauty, but don't let its calm exterior fool you. Its radio signals tell a far more intriguing story. Now, let's turn our attention to a cosmic jewel that defies expectations: Hoag's object, a galaxy so perfectly ring-shaped it looks almost artificial. At first glance, this celestial wonder appears tranquil, a serene loop of blue stars encircling a golden core, floating in the void like a cosmic bullseye. But beneath its picturesque facade lies a puzzle that has left astronomers scratching their heads: unexplained radio emissions that don't match its calm visual charm. Most galaxies fall into familiar categories: spirals, ellipticals, or irregular blobs. Hoag's object, discovered in 1950 by astronomer Art Hoag, is a rare ring galaxy, a type so unusual it makes up less than 0.1% of known galaxies. The ring, brimming with young, hot stars, orbits a central core of older, redder stars with a seemingly empty gap between them. How this structure formed remains debated. Was it a galactic collision, a gravitational anomaly, or something else entirely? But the real mystery isn't just its shape, it's the radio waves it emits. Unlike its peaceful optical appearance, Hoag's object broadcasts faint but peculiar radio signals. These emissions don't align with the usual suspects: no intense star formation, no active supermassive black hole at its core. Instead, the signals hint at hidden activity, perhaps relics of ancient mergers or unseen magnetic fields weaving through the ring. Some theories suggest the radio waves could be echoes of past interactions with smaller galaxies, long since absorbed, leaving only these faint whispers behind. What makes Hoag's object even more intriguing is its isolation. Most ring galaxies have neighbors whose gravitational tug might explain their structure, but Hoag's object floats alone, with no obvious partner to blame for its peculiar form or its radio anomalies. This solitude deepens the enigma: how did such a pristine ring form in the first place, and why is it singing this odd radio tune? Studying Hoag's object is like piecing together a cosmic cold case. Its radio signals offer clues to a history we can't yet fully reconstruct, a reminder that even the most serene corners of the universe can hide turbulent pasts. Up next, we'll dive into a galactic collision so dramatic, its radio signals scream across the cosmos, a story of chaos written in waves. Now, let's shift our gaze to a cosmic spectacle where chaos takes center stage. The Medusa merger, a violent dance of two galaxies colliding in a storm of radio waves. Unlike the serene mystery of Hoag's object, this is a universe of raw energy and turbulence, where gravity twists galaxies into monstrous shapes and sends shockwaves racing through space. When galaxies collide, it's not a quiet event. The Medusa merger, officially known as NGC 4194, is a prime example. A tangled mess of stars, gas, and dust, where two spiral galaxies have slammed into each other, stretching their arms into long, serpentine streams. These streams, glowing with radio emissions, resemble the writhing snakes of Medusa's hair, giving the merger its dramatic nickname. But what makes this collision truly fascinating isn't just the visual drama, it's the radio signals screaming from the wreckage. As the galaxies merge, their gas clouds compress, triggering bursts of star formation so intense they light up the radio spectrum. Supernova explode in waves, and magnetic fields twist into knots, amplifying the chaos. The result, a cacophony of radio waves that reveal the physics of cosmic crashes in real time. These signals aren't just noise, they're clues. By studying the Medusa merger's radio emissions, astronomers can trace how gas behaves during collisions, how shockwaves propagate, and even how supermassive black holes lurking in the cores of these galaxies awaken from their slumber. The merger's radio glow hints at the birth of new stellar nurseries, the death of massive stars, and the invisible forces reshaping galaxies on epic scales. Yet, the Medusa merger also poses questions. Why do some colliding galaxies erupt in radio fireworks while others stay relatively quiet? Could the angle of the collision or the galaxy's original structures play a role? Each signal from this cosmic train wreck adds a piece to the puzzle, helping us understand how galaxies evolve and how our own Milky Way might one day fare when it meets Andromeda. Up next, we'll explore another galactic oddity, one where rings of stars and gas spin perpendicular to the norm, creating radio patterns that defy expectations. The universe, it seems, never runs out of ways to surprise us. Now, let's turn our attention to a cosmic oddity that defies the usual rules of galactic architecture, the polar ring galaxy. Imagine a galaxy spinning like a top, but with a twist literally. Instead of a flat, orderly disk, this one wears a ring of gas and stars like a belt around its waist, but tilted at a sharp 90-degree angle to the main galaxy. It's as if the universe decided to bend the rules just to keep us guessing. These polar ring galaxies are rare, making up less than 1 in every 1,000 known galaxies, and their bizarre structure sends radio signals that leave astronomers scratching their heads. The rings themselves are thought to be the remnants of ancient cosmic theft, one galaxy ripping material from another during a close encounter, then flinging it into this perpendicular orbit. But here's the mystery. Why do these rings glow so brightly in radio waves? The answer lies in the chaos of creation. The gas in these polar rings is often rich with the raw ingredients for new stars, and as it collapses under gravity, it triggers bursts of star formation. Young, massive stars burn hot and fast, their deaths lighting up the radio spectrum with supernova explosions. Meanwhile, magnetic fields tangled in the ring's structure amplify the emissions, creating a radio signature unlike anything seen in typical galaxies. But the oddities don't stop there. Some polar ring galaxies show radio emissions that flicker or pulse, suggesting hidden activity, perhaps supermassive black holes stirring the pot or shockwaves rippling through the gas. Others have rings that seem too stable to have formed from a violent collision, raising questions about whether some of these structures could be primordial, dating back to the galaxy's birth. Studying these cosmic oddballs isn't just about solving a puzzle, it's a window into how galaxies grow and change. The polar rings' radio whispers tell us about the forces that shape galactic evolution, from gravitational tugs to the life cycles of stars. And with each new observation, we're reminded that the universe has a flair for the dramatic, turning even the simplest rules of physics into a spectacle. Next up, we'll dive into another galactic enigma, one where a tail of stars stretches across space like a cosmic tadpole, leaving radio clues in its wake. The universe, it seems, loves to keep us on our toes. Now, let's shift our gaze to another cosmic marvel that seems to defy expectations, the tadpole galaxy. Picture a galaxy with a tail so long and dramatic, it stretches across space like a celestial brushstroke, leaving behind a trail of radio whispers that tell a story of violent encounters and cosmic survival. This peculiar galaxy, officially known as UGC 1022, earned its nickname thanks to its striking resemblance to a tadpole, a bright, compact head followed by an elongated tail of stars and gas that spans nearly 300,000 light-years. But what makes this tail so fascinating isn't just its length. It's the radio signals it emits, clues to a dramatic past. The tail is the aftermath of a galactic collision, a moment when a smaller galaxy strayed too close and was torn apart by gravitational forces. As the victim galaxy was shredded, its stars and gas were pulled into this spectacular stream, now glowing brightly in radio waves. the signals reveal intense star formation as pockets of gas within the tail collapse under gravity, igniting new stars. These young, massive stars burn fiercely, their short lives ending in supernova that light up the radio spectrum. But there's more to the story. The tail's radio emissions also hint at something: unexpected magnetic fields woven into the gas, far stronger than astronomers anticipated. These fields act like cosmic amplifiers, boosting the radio signals and suggesting that even in the chaos of a collision, order can emerge. Some theories propose that these magnetic structures might help stabilize the tail, preventing it from dissipating entirely over time. What's truly remarkable is how the tadpole galaxy's tail serves as a time capsule. By studying its radio emissions, astronomers can piece together not just how this galaxy interacted with its unfortunate neighbor, but also how such encounters shape galaxies over billions of years. It's a reminder that even in the vastness of space, no galaxy is an island. Each one bears the scars and souvenirs of its cosmic relationships. Next, we'll explore another galactic wonder, one where spiral arms hide bursts of radio energy that defy easy explanation. The universe, it seems, has no shortage of mysteries waiting to be unraveled. Now, let's turn our attention to a cosmic masterpiece that's as mesmerizing as it is mysterious: the Whirlpool Galaxy. This stunning spiral, officially known as Messier 51, has long captivated astronomers with its graceful arms and vivid star-forming regions. But beneath its picturesque beauty lies a hidden enigma: sporadic bursts of radio energy that defy easy explanation. The Whirlpool Galaxy is no stranger to drama. Its elegant spiral arms, swirling with dust and young stars, are the result of a close encounter with a smaller companion galaxy. This cosmic dance triggered waves of star formation, lighting up the galaxy in visible light. But when astronomers tuned into its radio emissions, they discovered something far more unpredictable: sudden, intense bursts of radio waves flickering like cosmic Morse code. These bursts don't follow a regular pattern. They appear without warning, flare up briefly, and then vanish, leaving scientists scrambling to trace their origins. One leading theory points to the galaxy's supermassive black hole lurking at its core. While this black hole isn't as active as those in some other galaxies, it may occasionally belch out jets of high-energy particles. When these jets interact with surrounding gas, they could generate the erratic radio bursts we detect. But there's another twist. Some of these bursts seem to originate far from the galaxy's center, deep within its spiral arms. This raises the possibility of smaller, stellar mass black holes or neutron stars, remnants of exploded stars flaring up as they devour nearby material. These cosmic leftovers can unleash tremendous energy in short bursts, adding to the whirlpool's radio cacophony. What makes these signals so intriguing is their unpredictability. Unlike the steady hum of star formation or the persistent glow of the galaxy's core, these bursts are fleeting and chaotic. Studying them is like trying to catch lightning in a bottle, requiring patience and cutting-edge telescopes capable of capturing split-second cosmic events. As we peel back the layers of the whirlpool's secrets, we're reminded that even the most familiar galaxies can harbor surprises. Next, we'll venture into a galaxy where radio whispers seem to emerge from the shadows, a place where silence speaks volumes. Now, let's shift our gaze to a cosmic silhouette that's as enigmatic as it is iconic: the Sombrero Galaxy. Officially catalogued as Messier 104, this celestial wonder earns its name from the striking resemblance to a wide-brimmed hat with a glowing central bulge encircled by dark, sweeping dust lanes. But while its visual beauty is undeniable, the sombrero holds a quieter mystery: faint, elusive radio whispers emanating from those very dust lanes, signals that refuse to reveal their origins. Unlike the whirlpool's sporadic bursts, the sombrero's radio emissions are subtle and diffuse, like a faint static hiss woven into the fabric of the galaxy. These signals aren't tied to the galaxy's bright core or its bustling star-forming regions. Instead, they seem to seep from the shadowy dust lanes themselves, regions typically thought of as cosmic backwaters, where cold gas and dust obscure the light of stars behind them. What could be generating these faint radio murmurs? One possibility lies in the galaxy's turbulent past. The sombrero's distinctive dust lanes are likely the scars of ancient collisions, remnants of smaller galaxies swallowed long ago. As these mergers churn the galaxy's gas, they may have left behind pockets of charged particles or magnetized gas, quietly crackling with radio energy. Another theory points to cosmic rays, high-energy particles zipping through space, interacting with the dust lane's dense molecular clouds, producing radio waves as they collide. Yet the most puzzling aspect is the signal's uneven distribution. They're not uniform across the dust lanes but cluster in patches, like hidden radio beacons flickering in the dark. Some astronomers speculate these could trace the footprints of invisible stellar remnants, neutron stars or black holes lurking within the dust, their presence betrayed only by these faint emissions. Others wonder if they're evidence of exotic physics like dark matter interactions, though no definitive link has been found. The sombrero's silence is deceptive. Its radio whispers challenge our assumptions about where cosmic signals can arise, proving that even the darkest corners of a galaxy can hold surprises. Next, we'll dive into a celestial collision where radio noise reaches a crescendo, a galactic showdown that's anything but quiet. Now, let's turn our attention to a cosmic collision where silence is nowhere to be found: the antennae galaxies. These two spiral galaxies are locked in a violent embrace, tearing each other apart in a slow-motion dance that's anything but quiet. Their nickname comes from the long, streaming tails of stars and gas flung outward by the gravitational chaos, resembling the delicate antennae of an insect. But what truly sets this merger apart is the deafening radio chatter pouring from its heart, a cacophony of signals that tells the story of star formation on an epic scale. Unlike the sombrero's faint whispers, the antennae galaxies blast out radio noise with staggering intensity. This isn't just background static, it's the roar of countless newborn stars screaming into existence. The merger has compressed vast clouds of gas, triggering what astronomers call starburst regions, where stars form at rates hundreds of times faster than in our own Milky Way. Each of these stellar nurseries acts like a radio beacon, its young, massive stars heating the surrounding gas and accelerating particles to near light speeds, creating a symphony of radio waves. The most fascinating part, the radio signals map almost perfectly onto the galaxy's brightest starburst zones. It's as if the universe is highlighting the connection between violent galactic collisions and the birth of stars. But there's a twist. Some of the loudest radio emissions come from areas shrouded in dust, invisible to optical telescopes. Without radio observations, we'd miss entire chapters of this cosmic drama. Theories suggest that supernova explosions within these starburst regions amplify the radio noise further, as shockwaves rip through the gas, creating turbulent magnetic fields. Others point to the possibility of hidden supermassive black holes, their jets adding to the chaos. Whatever the exact mix, the antennae galaxies remind us that mergers aren't just destructive, they're also creative, forging new stars and reshaping galaxies in the process. This collision is a snapshot of our own Milky Way's future, when it eventually merges with the Andromeda galaxy billions of years from now. Up next, we'll explore another aftermath of a cosmic crash, a ring-shaped galaxy where radio signals echo like ripples from a stone tossed into a pond. Shifting our gaze to another cosmic spectacle, we encounter the Cartwheel Galaxy, a stunning ring-shaped structure that tells the tale of an ancient collision. Unlike the chaotic roar of the antennae galaxies, the Cartwheel whispers its history through delicate, reverberating radio signals, echoes of a dramatic encounter that reshaped it hundreds of millions of years ago. This galaxy's unique appearance comes from a smaller galaxy plunging straight through its center, sending shockwaves rippling outward like a stone dropped in a pond. These waves triggered bursts of star formation along the outer ring, while the inner regions bear the scars of the collision marked by faint but persistent radio emissions. What makes the cartwheel signals so intriguing is their longevity. They're not just remnants of the initial impact, but ongoing evidence of how galaxies heal and evolve over time. The radio waves here reveal something unexpected. The outer ring, glowing with young stars, isn't the only active region. Deeper inside, astronomers have detected subtle radio signatures from older stellar populations, suggesting that the collision stirred up activity across the entire galaxy, not just at the edges. This challenges the idea that ring galaxies are merely one-time fireworks displays. Instead, they're dynamic systems with long-term consequences. One theory proposes that the cartwheel's radio echoes are fueled by supernova remnants and turbulent magnetic fields left in the wake of the collision. Others speculate that hidden black holes, jostled awake by the impact, might be contributing to the signal. Either way, the cartwheel serves as a cosmic laboratory, showing how galaxies absorb violent shocks and gradually transform. Perhaps most fascinating is what this tells us about our own universe's history. Collisions like the cartwheels were far more common in the distant past, and studying its radio echoes helps astronomers piece together how galaxies grew and changed over billions of years. Up next, we'll dive into the jets of Centaurus A, where a supermassive black hole turns chaos into a high-energy light show. Now, let's zoom in on one of the most dramatic displays of cosmic power, the colossal jets of Centaurus A. This galaxy isn't just active, it's a full-blown particle accelerator on a galactic scale, blasting twin jets of superheated matter nearly 1 million light-years into space. These aren't gentle streams but violent outflows powered by a supermassive black hole at the galaxy's heart, and they're some of the most intense radio sources in our cosmic neighborhood. What makes Centaurus A's jets so special is their sheer energy. The black hole here, weighing in at around 55 million times the mass of our Sun, acts like a cosmic slingshot, hurling particles at nearly the speed of light. As these particles collide with surrounding gas, they emit powerful radio waves, painting the sky with giant, glowing lobes. But it's not just about raw power. These jets are a goldmine for scientists. They offer a front-row seat to extreme physics, from magnetic fields twisting like cosmic tornadoes to shock waves that accelerate particles to energies we can't replicate on Earth. One of the biggest puzzles is how these jets stay so tightly focused over such vast distances. Normally, you'd expect them to fan out or dissipate, but Centaurus A's jets remain razor-sharp, defying expectations. Some theories suggest the black hole's spin acts like a guidance system, while others point to intricate magnetic fields funneling the flow. Either way, it's a phenomenon that challenges our understanding of how energy behaves in the universe's most extreme environments. And here's where it gets even wilder. These jets might hold clues about how galaxies evolve. The energy they dump into surrounding space can heat up gas, stifling star formation and effectively putting the brakes on a galaxy's growth. In a way, Centaurus A's black hole isn't just a destroyer, it's a sculptor shaping its galaxy's destiny over billions of years. Up next, we'll turn our attention to Cygnus A, another radio giant whose beacon-like signals have fascinated astronomers for decades. Shifting our gaze across the cosmos, we arrive at Cygnus A beacon so bright in radio waves that it outshines nearly everything else in the sky. This isn't just another active galaxy, it's a titan, blasting signals so intense they've been studied for over half a century. At its core lies a supermassive black hole, but this one's a true overachiever, generating jets that stretch hundreds of thousands of light-years into space. What sets Cygnus apart is the sheer stability of those jets. Unlike chaotic outflows seen elsewhere, these streams are remarkably steady, like cosmic laser beams piercing the darkness. Scientists believe the black hole's immense gravity, weighing in at roughly 2 billion times the mass of our Sun, creates a sort of cosmic whirlpool, funneling matter into those precise jets. But here's the twist: even with all that power, the jets don't wobble or scatter. They stay locked on target, a feat that defies simple explanations. The secret might lie in the galaxy's unique environment. Cygnus A sits at the heart of a dense galaxy cluster, surrounded by hot gas that could act like a stabilizing sheath. Some theories suggest magnetic fields woven through the jets like invisible threads keep them tightly focused. Others propose that the black hole's spin acts like a gyroscope, maintaining their direction over mind-boggling distances. But the real puzzle: Cygnus A's jets are far brighter than they should be. Even with our best models, the energy output doesn't quite add up. Some researchers speculate there's hidden physics at play, perhaps particles being accelerated in ways we haven't yet imagined. It's a reminder that even the brightest cosmic landmarks can guard their deepest secrets. Up next, we'll dial down the intensity but not the intrigue as we examine the subtle, ever-changing whispers of Virgo A. Now, let's turn our attention to something quieter but no less fascinating: Virgo A, also known as Messier 87. Unlike the roaring jets of Cygnus A, this supermassive black hole speaks in murmurs, subtle and ever-changing radio signals that whisper secrets about the universe's most mysterious object. What makes Virgo A special isn't just its size, though its black hole is a staggering 6.5 billion times the mass of our Sun, but the way it behaves. After the Event Horizon Telescope captured that now iconic image of its shadow in 2019, scientists expected the radio emissions to follow predictable patterns. Instead, they found a symphony of variability, with signals that rise and fall in ways we're still struggling to decode. One of the biggest surprises: the black hole's radio emissions don't always match up with its other activity, like X-ray flares. Sometimes the radio waves flicker like a candle in the wind, while other times they stay eerily quiet. This mismatch hints at something deeper, perhaps gaps in our understanding of how black holes channel energy, or even new physics at play near the event horizon. Then there's the jet itself. While not as flashy as Cygnus A's, Messier 87 jet has its own quirks. Recent observations show it wobbling slightly, as if something unseen, maybe a second, smaller black hole, is tugging at it from the shadows. Others think the jet's instability could be caused by turbulence in the surrounding gas, like a river current fighting against hidden rocks. The real takeaway: even with the most advanced tools at our disposal, Virgo A reminds us that black holes are anything but simple. Every murmur, every flicker is a clue waiting to be unraveled. And as we'll soon see, the universe has even more surprises in store when we explore the giant radio lobes of Fornax A. Now, let's shift our gaze to another cosmic marvel: Fornax A, a galaxy whose radio lobes stretch across space like the echoes of a long-forgotten explosion. These colossal structures, each spanning hundreds of thousands of light-years, aren't just remnants of the past. They're active storytellers, revealing how galaxies evolve over billions of years. What makes Fornax A's lobes so intriguing is their age. Unlike the vibrant, energetic jets we've seen in younger galaxies, these lobes are fading, their radio emissions growing fainter as they slowly dissipate into the void. Think of them as cosmic campfires burning down to embers, their energy spreading thinner with time. But even in their twilight, they hold clues: the way these lobes interact with the surrounding intergalactic medium. Like ripples in a pond, helps astronomers map the invisible currents of gas and magnetic fields that shape entire galaxy clusters. Then there's the mystery of their asymmetry. One lobe appears brighter and more extended than the other, a puzzle that could trace back to the galaxy's turbulent history. Some suggest a past merger where another galaxy's gravitational tug warped the lobes unevenly. Others point to variations in the density of the surrounding space, like a whisper fading faster in thick fog than in open air. But perhaps the most fascinating lesson from Fornax is what it teaches us about endings. These lobes are a glimpse into the late stages of galactic activity. showing how even the most powerful engines, supermassive black holes, eventually quiet down. Yet, as we'll soon discover, the universe has a way of defying expectations, as seen in the unexpected revival of the Phoenix cluster. Now, let's journey deeper into the cosmos to witness something extraordinary: the Perseus cluster, a titanic gathering of galaxies where the very fabric of space hums with energy. Here, superheated gas, hotter than the core of most stars, fills the space between galaxies, and within this seething ocean, ripples of radio waves travel like cosmic sound waves. These aren't just random fluctuations, they're the echoes of violent eruptions from the cluster's central supermassive black hole, a monster with a temper that shapes its surroundings. Picture this: every few million years, the black hole awakens in a fury, belching out jets of energy so powerful they carve enormous cavities in the surrounding gas. These outbursts send shockwaves rippling outward, compressing and heating the gas even further. The result: vast, ghostly rings of radio emission that stretch across hundreds of thousands of light years, like ripples from a stone dropped into a pond. Except this pond is an intergalactic cauldron, and the stone is a black hole's tantrum. What's truly mind-bending is how these waves act as a cosmic record. By studying their patterns, astronomers can piece together the black hole's explosive history, like reading the rings of a tree to uncover past storms. Some of these ripples may date back hundreds of millions of years, offering a timeline of violence written in radio light. And here's the twist: these eruptions aren't just destructive. They're also regulators, preventing the gas from cooling too quickly and stifling the birth of new stars. It's a delicate balance between chaos and control, where the black hole plays both arsonist and firefighter. But the Perseus cluster has another secret. Some of its ripples don't match any known eruption, hinting at even older, more colossal explosions lost to time. Could there have been a cataclysm so immense it reshaped the entire cluster? Or is something else, something we don't yet understand, stirring the cosmic pot? As we turn our attention to the faint, elusive whispers of the Coma cluster next, remember, in the universe's grand symphony, even the quietest notes can hold the loudest mysteries. Now, let's shift our gaze to another cosmic giant, the Coma cluster, a sprawling metropolis of galaxies where silence isn't what it seems. Unlike the violent ripples of the Perseus cluster, the Coma cluster whispers. Its secret: a faint, ghostly radio halo, a diffuse cloud of emission that blankets the entire cluster like static from an old television, except this static is a cosmic puzzle. This halo isn't just background noise, it's a signal of electrons accelerated to nearly the speed of light, spiraling through magnetic fields that weave between galaxies. But here's the catch: these electrons shouldn't exist in such abundance. The energy required to keep them buzzing across millions of light years defies what our current models of dark matter predict. Dark matter, that invisible scaffold holding galaxies together, is thought to shape these clusters gently, yet the Coma cluster's radio halo suggests something far more turbulent. One theory points to ancient collisions. Over billions of years, galaxies in the cluster have smashed together, sending shockwaves through the surrounding gas. These shocks could have pumped energy into electrons, lighting up the halo. But there's a problem: the halo is too uniform, too smooth. If collisions were the culprit, we'd expect patchy, uneven emission. Instead, the Coma cluster's halo glows with eerie consistency, as if something else, something unseen, is stirring the pot. That's where dark matter theories hit a wall. Some researchers propose exotic particles within dark matter could be decaying, releasing energy that fuels the halo. Others wonder if the cluster's magnetic fields are far stronger than we've measured, twisting and amplifying the radio waves in ways we don't yet understand. Whatever the answer, the Coma cluster's hidden noise is a direct challenge to our understanding of the universe's invisible architecture. As we peel back the layers of this mystery, remember, sometimes the quietest signals shout the loudest questions. And with that, we're ready to dive into the next enigma, the Bullet Cluster, where two cosmic titans collided, leaving behind a trail of clues about dark matter's true nature. Now, let's turn our attention to one of the most dramatic cosmic collisions ever observed, the Bullet Cluster. This isn't just a spectacle of galaxies crashing into one another. It's a cosmic crime scene, and the evidence it leaves behind could rewrite our understanding of dark matter. When two galaxy clusters collide, the result is chaos on an unimaginable scale. But the Bullet Cluster is special because it didn't just collide, it punched straight through, leaving a trail of clues in its wake. The radio signatures here are like fingerprints, revealing secrets about the invisible hand shaping our universe. First, the visible stuff, the hot gas between galaxies. As the clusters collided, this gas slammed together, heating up so intensely that it glowed in X-rays. But here's the twist, the radio waves tell a different story. While the gas got stuck in the middle, something else kept moving, something we can't see. That something is dark matter. How do we know? Because the gravitational lensing effects, where the cluster's mass bends light from distant galaxies, show that most of the mass isn't where the gas is. It's out ahead in two distinct blobs. That means dark matter, which doesn't interact with gas or light, sailed right through the collision like a ghost, while ordinary matter got tangled up in the wreckage. This is some of the strongest evidence we have that dark matter is real. If dark matter were just an illusion, a flaw in our understanding of gravity, then the mass and the gas would stay together. But they don't. The Bullet Cluster proves they behave differently, and that's a game changer. Yet mysteries remain. Why do some radio emissions linger where the gas is? Could there be faint, unseen particles interacting in ways we haven't detected? The Bullet Cluster doesn't just confirm dark matter, it challenges us to dig deeper. And with that, we're ready to explore another cosmic heavyweight, the El Gordo Cluster, where the universe's most massive collision is still echoing across space. Now, let's shift our gaze to a true titan of the cosmos, El Gordo, the universe's most massive known galaxy cluster. This colossal structure isn't just big, it's a roaring powerhouse of radio emissions that challenge our understanding of how such giants form in the early universe. El Gordo, which fittingly means the fat one in Spanish, lives up to its name. Located around 7 billion light-years away, it's a cosmic heavyweight packing the mass of 3 million billion suns. But what makes it truly fascinating isn't just its size. It's the intense radio waves screaming from its core. These emissions aren't just background noise, they're the echoes of a violent past, a relic of the cluster's turbulent formation. When astronomers first studied El Gordo, they noticed something unusual. The radio signals weren't uniform. Instead, they formed vast, arc-like structures, hinting at shockwaves rippling through the cluster's hot gas. These shocks are like cosmic fingerprints, evidence of a dramatic collision between two smaller clusters that merged to create this behemoth. The energy released in that crash was so immense it still reverberates today, lighting up the radio spectrum. But here's where it gets even more intriguing. El Gordo shouldn't exist, at least not according to some models of the early universe. Its sheer size and the timing of its formation push the limits of what we thought was possible. If clusters this massive were already forming when the universe was half its current age, it forces us to rethink how quickly matter clumped together in those ancient times. And then there's the dark matter puzzle. Like the Bullet Cluster, El Gordo's gravitational lensing reveals that most of its mass isn't where the hot gas glows. Instead, it's concentrated in two distinct regions, further proof that dark matter is real, and that it plays a starring role in shaping these cosmic giants. Yet mysteries linger. Why are the radio emissions so much brighter than expected? Could there be unseen particles or magnetic fields amplifying the signal? El Gordo doesn't just roar, it asks us to listen closely because its secrets might rewrite the story of how the universe builds its largest structures. And with that, we're ready to explore another cosmic enigma, the Phoenix Cluster, where death and rebirth collide in a way no one predicted. Now, let's turn our attention to a cosmic phoenix rising from the ashes, the Phoenix Cluster. This galaxy cluster defies all expectations, proving that even in the quietest corners of the universe, life can reignite in the most spectacular ways. The Phoenix Cluster earned its name for a reason. Like the mythical bird, it's a story of rebirth. Most galaxy clusters have cores that are considered dead. Their central galaxies have long since exhausted the fuel needed to form new stars, leaving them dark and dormant. But the Phoenix Cluster is anything but dead. At its heart, it's a frenzy of activity, pumping out radio signals so intense they've left astronomers stunned. What makes this cluster so extraordinary is its central supermassive black hole. Unlike most black holes in similar clusters which grow quiet over time, this one is anything but dormant. It's feeding voraciously, spewing jets of energy that heat the surrounding gas. But here's the twist: instead of suppressing star formation, as these jets usually do, the Phoenix Cluster's outbursts seem to be triggering it. Radio observations reveal vast reservoirs of cool gas swirling around the core, a rare sight in clusters of this age. Normally, this gas should be too hot to collapse into new stars, but the Phoenix Cluster's unique conditions are creating pockets where star birth can thrive. It's as if the black hole's violent outbursts are stirring the cosmic pot, creating the perfect recipe for rebirth. This discovery turns conventional wisdom on its head. For decades, astronomers assumed that once a cluster's core went quiet, it stayed that way. The Phoenix Cluster shatters that assumption, showing that even the most dead galactic centers can roar back to life under the right conditions. But the mystery deepens. Why is this cluster so different? Is it a rare fluke, or are there others like it waiting to be discovered? The Phoenix Cluster doesn't just challenge our understanding, it forces us to reconsider what's possible in the life cycle of galaxy clusters. And with that, we're ready to uncover another enigma, the bizarre case of the missing black hole in Able 2261. Now, let's unravel one of the most baffling cosmic mysteries, the case of the vanishing black hole in Able 2261. Galaxy clusters are supposed to have supermassive black holes anchoring their cores, but this one seems to have gone missing without a trace. Able 2261 is a colossal cluster located about 3 billion light-years away, and its central galaxy should host a black hole weighing in at billions of times the mass of our Sun. Yet, despite exhaustive searches, astronomers can't find it. Radio observations have only deepened the puzzle. Instead of a single, powerful source of emissions, they've detected a diffuse, sprawling radio glow stretching across thousands of light-years. It's as if the black hole was once there and then just disappeared. So where did it go? One leading theory suggests a dramatic galactic merger. When two galaxies collide, their central black holes can spiral toward each other, eventually merging in a cataclysmic event that sends ripples through space-time. But sometimes the recoil from such a merger can kick the newly formed black hole clear out of the galaxy entirely. If that happened here, Able 2261 black hole might now be drifting through intergalactic space, invisible to our telescopes. The radio emissions we see could be the aftermath, a ghostly echo of the black hole's last violent interactions before it was ejected. Another possibility. The black hole might still be lurking in the core, but it's gone dormant, starving so completely that it's no longer emitting detectable radiation. Either way, this enigma forces us to rethink how black holes behave in the most extreme environments. What makes Able 2261 even more intriguing is that its central galaxy is unusually puffy, with stars spread out far wider than expected. That could be another clue, evidence of a gravitational tug-of-war that reshaped the galaxy during the black hole's disappearance. For now, the mystery remains unsolved, but every observation brings us closer to understanding whether supermassive black holes can truly vanish, or if they're just hiding in plain sight. And with that, we're ready to dive into the cosmic chaos of Stephan's quintet, where colliding galaxies create a symphony of radio signals unlike anything else in the universe. Now, let's turn our attention to a cosmic collision of epic proportions: Stephan's quintet. This tight-knit group of 5 galaxies, located nearly 300 million light-years away, is a chaotic masterpiece of gravitational interactions. But what makes it truly special isn't just the visual spectacle, it's the symphony of radio signals pouring out from this galactic pile-up. 4 of these galaxies are locked in a slow-motion dance, their gravity pulling them closer over millions of years. The 5th, it's actually a foreground galaxy just along our line of sight, but the other 4 are tearing each other apart in real time. The result? A cacophony of radio emissions that tell the story of gas clouds being shocked, compressed, and heated to extreme temperatures. One of the most striking features is the enormous shockwave rippling through the interstellar gas. As galaxies collide, their gas clouds slam together at speeds of millions of miles per hour, creating a turbulent sea of radio waves. This isn't just noise, it's a snapshot of cosmic evolution in action. The radio signals reveal how these violent interactions trigger bursts of star formation, with newborn stars lighting up like fireworks in the chaos. But there's another twist. At the heart of this maelstrom, one galaxy in UC 7319 hosts an active supermassive black hole. Its jets of high-energy particles add another layer to the radio cacophony, intertwining with the collision's natural chaos. It's like listening to an orchestra where every instrument is playing a different tune, yet somehow it all comes together to tell a single, breathtaking story. What makes Stephan's quintet so valuable to astronomers is that it's a preview of our own galaxy's future. Billions of years from now, the Milky Way and Andromeda will collide in a similar spectacle. By studying this quintet, we're essentially peering into a cosmic crystal ball, learning how galaxies merge, evolve, and reshape the universe around them. And with that, we're ready to close our journey with the faintest whispers of all the radio signals from the Hubble Deep Field, where the universe's most distant galaxies reveal secrets from the dawn of time. Now, let's journey to the very edge of the observable universe, where the faintest whispers of radio signals carry echoes from the dawn of time. The Hubble Deep Field, a tiny patch of sky no larger than a grain of sand held at arm's length, reveals galaxies so distant their light has traveled for over 13 billion years to reach us. But it's not just their ancient light that captivates astronomers, it's the delicate radio signals they emit, offering clues about the universe's infancy. These signals are incredibly faint, like trying to hear a whisper in a hurricane. Yet, with advanced telescopes like the Atacama Large Millimeter Array, scientists have begun to decode them. What they've found is astonishing. These distant galaxies, seen as they were just a few 100 million years after the Big Bang, were already bustling with activity. Their radio emissions suggest intense star formation, with newborn stars igniting in clouds of primordial gas. But there's a puzzle hidden in these whispers. The signals don't match what models predict for such early galaxies. Some are brighter than expected, hinting at unknown processes that accelerated star formation. Others show strange chemical signatures, suggesting the first heavy elements were forged in ways we don't yet understand. It's like finding pages missing from the universe's baby album, gaps in our story of how everything began. One of the most tantalizing discoveries is the presence of carbon monoxide in these ancient galaxies. This molecule, usually associated with later cosmic eras, shouldn't exist in such young galaxies. Its detection forces us to rethink how quickly the universe enriched itself with heavy elements. Were there supernovae exploding sooner than we thought? Or did some unknown mechanism spread these elements faster? The Hubble Deep Field's whispers also hint at the seeds of cosmic structure. The faint radio signals trace the web of gas that would eventually collapse into galaxies and clusters. By mapping these signals, astronomers are piecing together how the universe grew from a smooth, hot soup of particles into the intricate tapestry we see today. As we close our exploration of these 50 unexplained signals, the Hubble Deep Field reminds us that every whisper from the cosmos carries a story. From the violent collisions of Stephan's quintet to the faint murmurs of the earliest galaxies, these mysteries push us to keep looking, listening, and questioning. The universe is far from done surprising us, and that's what makes the search so thrilling. If you've enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell so you never miss out on the next cosmic mystery we uncover. And tell us in the comments which of these 50 signals left you the most awestruck. Until next time, keep gazing upward. The universe has so much more to reveal. As we wrap up this cosmic journey, one thing becomes undeniably clear. The universe is brimming with mysteries that refuse to fit neatly into our textbooks. From the eerie echoes of the WOW signal to the faint whispers of the Hubble Deep Field, these 50 unexplained signals challenge everything we think we know about space. They're not just anomalies, they're cosmic breadcrumbs leading us toward questions we haven't even thought to ask yet. What ties them all together? A relentless push against the limits of our understanding. Every strange frequency, every burst of energy we can't explain, forces astronomers to rethink the rules. Whether it's the bizarre behavior of fast radio bursts or the unexpected chemistry of ancient galaxies, these signals remind us that the universe is far wilder, far more inventive than our theories often allow. And that's the beauty of it. Each mystery solved opens the door to 10 more, keeping the flame of curiosity alive. Who knows what we'll discover next? Maybe a signal that finally reveals extraterrestrial intelligence, or a cosmic phenomenon so bizarre it rewrites physics itself. The only way to find out is to keep listening, keep exploring, and most importantly, keep wondering. So, what was your favorite signal from this list? Did the Lorimer burst leave you stunned, or were you captivated by the enigma of Tabby's star? Drop your thoughts in the comments below. We'd love to hear which cosmic puzzle hooked you the most. And if you're hungry for more deep space mysteries, don't forget to hit that like button, subscribe, and ring the notification bell. The universe has plenty more secrets to share, and we'll be here to uncover them together. Until next time, keep looking up. The stars are just getting started.